Most people assume large ships are fast because they're powerful. More engine, more speed, less fuel per mile. Naval architects discovered something different. At cruising speed, a ship's engines aren't fighting friction. They're fighting the wave the hull creates just by moving through water. That wave radiates energy outward continuously, and generating it consumes up to 60% of total engine output. The bulbous bow solves that problem by creating a second wave designed to cancel the first one. It's destructive interference, the same principle as noise-canceling headphones, built into 20 tons of steel below the waterline. Here's exactly how it works. Water doesn't move out of the way when a ship passes through it. It gets pushed. And the hull of a moving vessel displaces water continuously, forcing it outward and downward along the hull surface, then allowing it to return behind the stern. That process creates two distinct resistance forces acting on the hull simultaneously, and understanding which one dominates at cruising speed is the only way to understand why the bulbous bow exists at all. That is where the physics begins. The first force is friction drag. As the hull moves through water, fluid in direct contact with the steel surface clings to it, a thin boundary layer that the hull carries along with it through the water. The energy cost of pulling that layer through the surrounding water constitutes friction drag. It scales with wetted surface area and with speed. More hull surface in contact with water means more friction drag. For most of maritime history, friction was the resistance force naval architects spent the most effort reducing. Smooth hull coatings, anti-fouling paint, polished underwater surfaces, all aimed at minimizing energy lost to friction between hull steel and seawater. The second force is wave-making resistance. When a hull pushes water outward, the displaced water doesn't simply flow around the hull and return silently. It forms a wave system, a structured pattern of crests and troughs radiating outward from the bow and stern, carrying energy with it continuously across the water surface. Generating that wave costs energy. A portion of the ship's thrust doesn't move the hull forward. It goes into building and sustaining the wave pattern the hull creates just by moving. That energy leaves the ship and propagates outward. It doesn't return. At low speeds, a wave-making resistance is small. Friction drag dominates. A slow-moving harbor tug is fighting friction far more than it is fighting waves. But as ship speed increases, wave-making resistance grows disproportionately, not linearly, but approximately with the square of speed. Double the speed and wave resistance increases roughly fourfold. At the cruising speeds of large commercial vessels, supertankers, container ships, bulk carriers, wave-making resistance accounts for between 40 and 60% of total hull resistance. It is the dominant force those engines are working against. At cruising speed, the engines aren't primarily fighting the water they're moving through. They're fighting the wave they're generating just by existing in it. Reducing wave-making resistance is the highest value target in commercial hull design. Naval architects quantify this relationship using the Froude number, a dimensionless ratio comparing a ship's speed to the square root of its waterline length. What it captures is the point at which wave-making resistance begins to dominate total hull resistance. Below a certain Froude number, friction leads. Above it, waves lead. Large commercial vessels at cruising speed operate firmly in the wave-dominated regime. That is the environment the bulbous bow was designed to address. Here is the paradox at the center of the design. The bulbous bow is a steel protrusion extending forward from the hull below the waterline. Welding it to the hull increases the vessel's total wetted surface area. More wetted surface area means more friction drag, not less. The bulb makes that component of resistance measurably worse. And by every principle of friction-focused hull design, attaching a bulb to the bow is the wrong direction entirely. But friction drag is not the problem the bulb is solving. Wave-making resistance is. The bulb reduces wave-making resistance through a mechanism that has nothing to do with streamlining, nothing to do with surface smoothness, and everything to do with what happens when two wave systems occupy the same water at the same moment. The mechanism only functions within a specific speed range. The bulb's geometry, its size, shape, and position relative to the bow, is calculated for a design speed. The cruising velocity at which the pressure wave the bulb generates is timed to interact with the hull's bow wave in a precise way. At that speed, the two wave systems meet in a configuration that partially cancels their combined wave energy. Below design speed, that configuration shifts. Above design speed, it shifts further, and the interference that was reducing wave energy now reinforces it instead. Push a supertanker optimized at 14 knots to 17 knots, and the bulb's wave interaction pattern moves outside the useful range. Wave-making resistance increases. Fuel consumption rises above what an equivalent hull without the bulb would burn at the same speed. The shape designed to save fuel at the correct speed actively costs fuel at the wrong one. The bulbous bow saves fuel at exactly one speed. Push the engines above that threshold, and the same shape that delivers up to 15% fuel savings starts costing extra instead. Here's the physics that makes both outcomes possible. And two waves meeting in the same water don't add together the way solid objects do. They interfere. When a crest from one wave system arrives at the same point as a trough from another, the two don't stack, they partially cancel. The water surface at that point rises less than either wave would produce alone. The combined wave is smaller, and a smaller wave carries less energy outward from the hull. That energy reduction is the fuel saving. That mechanism is destructive interference, and it is what the bulbous bow is engineered to produce. The hull generates its bow wave from the leading edge of the hull at the waterline, the point where the hull first meets undisturbed water and begins pushing it aside. That impact creates a pressure buildup at the bow, which propagates outward as a wave crest. Behind it follows a trough, and then another crest near the stern. The entire wave pattern radiates energy continuously as the ship moves. The bow wave crest is the largest and most energetically costly component of that system. Reducing it reduces the total energy cost of moving the hull through water. The bulbous bow sits below the waterline, ahead of the hull's bow wave origin point. As the ship moves, the bulb displaces water and generates its own pressure wave, a crest that propagates upward and outward from the bulb's leading surface. At the design speed, the geometry of the bulb is calculated so that this crest arrives at the water surface in a specific phase relationship with the hull's bow wave crest, not aligned with it, offset from it by half a wavelength. So the bulb's crest arrives where the hull wave's trough would be. And the hull wave's crest arrives where the bulb's trough follows. The two systems partially cancel at their point of interaction. The combined bow wave is reduced in height and energy content compared to what the hull would generate without the bulb present. The calculation matters precisely because partial cancellation is the realistic outcome, not total elimination. The bulb doesn't erase the bow wave. It reduces it by a margin that depends on how accurately the bulb's geometry was matched to the design speed, how close the actual operating speed is to that design point, and the specific hull form being modified. The wave resistance reduction at design speed is real and measurable. Untowing tank experiments produce wave pattern photographs that show the difference directly. A hull with a correctly designed bulb generates a visibly smaller bow wave than an identical hull without one at the same speed. Now, the trade becomes clear. The bulb increases wetted surface area. Friction drag goes up by a calculable amount based on the additional steel surface in contact with water. Simultaneously, the destructive interference reduces wave-making resistance. That component goes down by a larger amount at design speed. The net result is a reduction in total hull resistance despite the friction penalty. The bulb costs something in one column and saves more in another. At design speed, the wave resistance column wins. The engineering judgment embedded in the bulbous bow is not that friction drag doesn't matter, and it's that at cruising speed, wave-making resistance matters more, and a shape that trades friction for wave reduction produces a net gain that translates directly into fuel burned per mile. David W. Taylor understood this in 1907. Taylor was a naval architect working for the United States Navy, conducting systematic hull resistance experiments in a purpose-built towing tank, a long channel of still water in which scale models of hulls could be towed at controlled speeds while instruments measured resistance forces precisely. Taylor tested hull forms with and without a forward protrusion below the waterline and measured the wave patterns each produced. The results showed that a correctly proportioned bulb reduced the bow wave and lowered total hull resistance at the target speed. The USS Delaware, a battleship, was built incorporating Taylor's bulb design. The resistance reduction was documented. The physics was not in dispute. The noise-canceling headphone sitting in a traveler's bag operates on identical mathematics. A microphone samples ambient noise. Electronics generate a sound wave of equal amplitude and opposite phase. The two waves meet at the listener's ear and cancel. The mechanism is destructive interference applied to sound rather than water. Consumer electronics commercialized that principle in the 1980s. Naval architecture proved it in a towing tank 80 years earlier, then watched commercial shipping ignore it for half a century. The physics was proven in 1907. The shipping industry took 50 years to act on it. Here's why that gap existed, and what finally closed it. The gap between proof and adoption wasn't ignorance. Naval architects read Taylor's work. The towing tank data was published, peer-reviewed, and available to every shipyard producing commercial vessels in the decades after 1907. The physics wasn't contested. What was contested was the economics. And for 50 years, the economics didn't favor the modification. Commercial shipping operates on margins measured in fractions of a percent per voyage. A ship owner in 1920 or 1940, facing the decision to modify a hull with an unproven commercial track record, one that required dry docking, structural modification, and additional steel, needed a fuel saving large enough to recover that cost within a commercially acceptable time frame. Fuel was cheap, the payback window was long, the modifications stayed in the literature. The 1960s changed the calculation. Fuel costs rose. And voyage distances on major trade routes, Europe to Asia, the Americas to Japan, were long enough that fuel efficiency improvements compounded into significant money per voyage. Japanese shipyards, competing aggressively for commercial contracts in the post-war decades, began applying bulbous bow designs to merchant hulls systematically. European yards followed. The retrofit economics that had never worked at 1930s fuel prices worked clearly at 1960s fuel prices. The physics hadn't changed. The spreadsheet had. Retrofitting an existing vessel required dry docking the hull, cutting into the bow structure, and welding the bulb onto the modified forward section. That process cost money and time, but on long-haul routes, the fuel saving recovered the retrofit cost within 2 to 3 voyages on large vessels, not 2 to 3 years. In 2 to 3 voyages. At that payback rate, the decision wasn't marginal. It was straightforward. Shipyards that had spent decades building hulls without bulbs began offering retrofit programs. New construction incorporated the bulb as standard from the keel up. Modern bulb design bears little resemblance to Taylor's original geometry in its precision, though the underlying physics is unchanged. Computational fluid dynamics software allows naval architects to simulate the complete wave interaction pattern around a hull before a single plate of steel is cut. The bulb's diameter, length, cross-sectional shape, and vertical position relative to the waterline are all variables optimized against the specific vessel's operating profile. Its design speed, its loaded versus ballast displacement, its primary trade route, and the sea states it will typically encounter. A slow bulk carrier moving grain at 12 knots requires a different bulb geometry than a container ship running at 22 knots. The same principle, different execution. Because design speed determines everything and no two vessel types share the same operating envelope. The fuel saving that results from a correctly designed and correctly operated bulbous bow falls between 5 and 15% of total voyage fuel consumption. The lower end reflects vessels that operate across a wider speed range, spending time above and below their design speed. where the bulb's interference pattern moves off the optimal configuration. The upper end reflects large, slow-moving tankers and bulk carriers that maintain consistent cruising speeds on long ocean passages, holding the hull close to design speed for the majority of each voyage. Up to 15% isn't a marketing figure. It's the documented ceiling for the vessels in operating conditions where the bulb's interference is most precisely maintained. At the scale of global shipping, those percentages carry enormous weight. The world's commercial fleet burns approximately 300 million tons of fuel annually. A 10% fleet-wide efficiency improvement from hull optimization represents 30 million tons of fuel not burned per year, more than the total annual fuel consumption of most individual nations. The bulbous bow is the single most fuel-efficient modification ever applied to commercial hull design. It achieved that status not through new materials, not through more powerful engines, not through revolutionary propulsion technology, but through a geometric shape below the waterline that most passengers and crew never see and most port workers never notice. The next generation of hull efficiency technology follows the same counterintuitive logic. Air lubrication systems pump a continuous layer of microbubbles along the underside of the hull, reducing friction between the steel surface and the water. Friction drag goes up in one sense. The system requires energy to generate the bubbles, while going down in another because the bubbles reduce the contact resistance between hull and water more than the pumping costs. The net saving falls between 5 and 10% on suitable hull forms. The same trade the bulbous bow makes between two drag components, applied to a different layer of the resistance problem. On a 20-ton shape below the waterline, invisible from the dock, unknown to every passenger who has ever stood at a ship's bow watching the ocean pass, saving more fuel across the global fleet each year than most countries consume entirely. The physics has not changed since David Taylor measured wave patterns in a towing tank in 1907. What changed was the fuel bill.